So let's do a quick recap of what we talked about last time. So we started talking about GPS. And we said that the GPS is a sensing technology that specifically enables us to do localization and some odometry using signals from satellites that are orbiting the Earth. And by localization, we basically mean to determine the 3D position of the receiver. And it's useful because if you have a map, then you can use your localization data to exactly pinpoint your location on the map. Okay? And odometry, remember, it's basically information about how we're moving. So basically, you can think of it as the 3D velocity vector of the receiver, for instance. That's what we mean by odometry. And how does it work at a very high level? At the core of it is this concept of ranging using time of flight measurements, which is a very simple concept. So assume, and it's not only GPS, right? This is a very, very general concept, and you would see it throughout the class that many other sensors that we talk about also at the core use this idea of ranging via time of flight, which is basically you have a transmitter and a receiver, okay? And the transmitter sends some signal, right? In the case of the GPS, it's an electromagnetic wave that it transmits. And here I'm showing it as a pulse, but it can be a continuous signal. I mean, there's very different ways of doing it. But the concept is you send something, and it travels through a medium at some velocity, call it c, and then it reaches the receiver, right? Now, if the transmitter and the receiver have synchronized clocks, and if they have somehow agreed on where the signal was transmitted, okay? And I haven't told you how yet, but let's just assume that there's this time t0 that is known to the transmitter and the receiver, and they have agreed that at t0, I'm going to send you a signal. And then the receiver waits to receive that signal, and some time has passed for this to travel through the medium, and the receiver checks the clock when it receives it, and it sees, okay, it's t0 plus tau. So tau must have been the travel time, or the time of flight of this signal from the transmitter to receiver. And then if the receiver measures tau, right, and then it also the speed of the travel of that signal through the medium is known. So for instance, if it's an electromagnetic wave in free space, we know exactly what the speed of light is. So you just multiply that time of flight by the velocity or the speed, and that gives you range. So you go from a time measurement to a distance measurement. So time and distance are coupled through this basically velocity here. Okay? So that's again, simple concept, but very foundational to how GPS and many other sensors work. And then how do you use it? So then the way it's used specifically for GPS is this idea of localization via range measurements. So in a simple 2D example, we saw that if you have two transmitters, say two satellites, at two known positions, P1 and P2, okay? And in the 2D case, these are two vectors. In the 3D case, these are 3D vectors. So P1, P2 are known. And then the receiver, if it can measure its range or distance from each of them, then the location of the receiver relative to each of the transmitters has to be on a circle which is centered at the position of the transmitter with a radius that is equal to the distance from that. So you get one circle around P1, another circle around P2, and they will intersect at 2 points, call them A and B. So then the actual position of the receiver has to be either at A or at B. There's still some ambiguity here, and we talked about different ways that you can disambiguate. For instance, if you have more transmitters, if you add one more, then there's going to be a third circle, and then they would intersect at just 1 point. That's one way. So add more measurements. Basically, that will break the ambiguity for you. Or if you have some constraints that you can add to the problem, for instance, you know that your receiver is on the surface of the Earth, which is this ellipsoid, and then include that as a constraint to the problem, then you can also break the ambiguity and determine the position exactly. Okay? So that's the core concept or principle of operation of the GPS. But very specifically, for it to work, three things need to happen, right? So it's kind of like a three-step process. First, the receiver needs to, as it's called, acquire a number of satellites. So this acquisition step, what it means is that it needs to receive signals from them, and from the signals be able to find the exact position of the satellites. And how many are needed? At least 4. So it needs to find at least 4 satellites and be able to determine the exact position. So P1, P2, P3, and P4 need to be estimated or determined by the receiver. That's step 1. Then it needs to find its range to each of these 4 satellites using this concept of time of flight measurements. So that's a step 2. So find the range to each of the satellites via the TOF principle. So that's 4 numbers, R1, R2, R3, R4, right? That's the second estimation step. And then the third step, so now you have the positions, you have the ranges, and then you need to solve this essentially geometric problem of finding the intersection of these spheres, right? The intersection point, which is the position of your receiver. So you would use the positions, P1 to P4, and the ranges, R1 to R4, to estimate the receiver position. We call it P sub R, which is a 3-vector, right? We're localizing in 3D, so X, R, Y, R, Z, R. And remember we said there is a 4th parameter that needs to be estimated, which is the clock offset, tau sub D of the receiver with respect to the GPS reference clock. And the reason that there is this tau sub D is that if you go back to the time of flight measurement principle, we said that the underlying assumption here is that the clock of the transmitter and the receiver are perfectly synchronized, right? So when they agree that I'm going to transmit at t equals t0, t equals t0 is the exact same time for the transmitter and the receiver. In real world, that's never the case. It is the case between the GPS satellites. So the GPS satellite systems, these 30-something satellites that are orbiting the Earth, they have very fancy, super well synchronized clocks between them. So that's kind of like your standard reference clock system of the GPS. But our receivers, our phones, our laptops, our car GPS systems, or whatever receivers we have, they do not have perfect clocks. These are these cheap electronic clocks based on oscillators and things like that. So our clock is always going to be offset from the GPS reference clock. So there is going to be the time of flight that we measure is not just t0 plus t, it's plus tau. It's t0 plus tau plus our timing delay, called it tau sub d, which is the offset with respect to the reference clock. So for the GPS to work, if we do not account for tau sub d, that's going to go into our range measurements, of course, right? So our range becomes, instead of just c times tau, it becomes c times tau plus this error term, which is c times tau d. So our ranges would be off, and we saw that if your ranges are off, then your position is going to be inaccurate. And it just breaks the system. So you have to also estimate and account for your timing offset. And that's why at least 4 satellites are needed, right? Because you're estimating 4 parameters, x, y, z, and tau, so you need 4 measurements at least. In principle, the receivers usually try to acquire as many satellites as they can. They typically work with like 6, 7, or 8, depending on how many are available at the time. And then that just adds more measurements and makes it more accurate. But if it cannot find at least 4 satellites, your GPS wouldn't work. It will just try to acquire more. And that's sometimes in challenging cases where you do not have line of sight to those number of satellites, you might have experienced that your GPS just takes a very long time to get you the first position fixed because it's just trying to find the 4 reliable satellites. Okay, so this is super high level. Now, what we're going to do today and the next lecture is we're going to go deep dive into these 3 steps, like really go deep down and see how each of these work. How do you find estimate the position of these satellites that are orbiting the Earth? How do you do actual time of flight measurements to each satellite? And then how do you use these measurements to estimate your position and timing offset? Okay? Any questions? No. All right, let's continue. So here's where we are on this slide. So again, the receiver needs to basically estimate the satellite locations in orbit, and that is calculated from what is called the ephemeris data. Okay, I'll tell you what it is, but that's the terminology used for it. It's called the ephemeris data. And then the ranges, or the time of flights, are calculated from what is called ranging codes. Okay, again, don't worry if these are not familiar. We're going to talk about it in a lot of detail. Okay, before that, let's start from a high-level overview of the GPS system. So this is just a picture showing kind of like the constellation of the GPS satellites that orbit the Earth. And the first satellite was launched in 1978. And the system became fully operational in 1995. And fully operational, what it means is that it basically started getting full coverage around the globe, you know, with all the good properties that we talked about that were required of the GPS system. It nominally consists of 24 satellites in 6 equally spaced orbital planes. So each color here is an orbital plane, like this red one, for instance. And as you see, there's like 4 little dots on it, and those are the nominal positions of the satellites. And this is nominal. In reality, there's more. There's 30-something, like 36, 37 at a time, usually satellites orbiting the Earth. But 24, if it goes below 24, then we might not get like full coverage. And so that was like designed for at least like 24 satellites orbiting. And these are at an altitude of 20,200 kilometers above the Earth, okay? And they're orbiting the Earth. So it's very important that the location of these satellites relative to the Earth is not constant. They're like rotating around the Earth. Here's a cool visualization, if I can open it. So this is cool. So this is here, this little red dot on the surface of the Earth. That's, say, your receiver. And it kind of sees over time as the Earth rotates and as the satellites are orbiting the Earth, those lines are the line of sights to the satellites. So it kind of shows you like, okay, you're alternating between like 6, 7, 8, 9, 10, you know, how many visible satellites you have. But the point is, at every given time, that number is always above 4. And that was an important design principle of the GPS system. And it's not trivial, by the way. Like it's very interesting engineering went into the actual design of the GPS constellation and how many orbital planes you want to have, how many satellites you want to have per orbit to really guarantee without launching too many satellites, because these are very, very, very expensive, right? We are talking like billions of dollars per satellite. And there's like maintenance for each of them, and you don't want to like blow up the cost of the system out of proportion. So engineers came up with like a minimal set of satellites with very specific orbit trajectories around the Earth to always guarantee 4 satellites inside. It's pretty interesting in that regard. Okay, so it's owned by the U.S. government, the GPS system, and operated by the U.S. Space Force. Now, towards the end of the chapter, we'll talk about now, the GPS is not the only satellite positioning system. Different countries like the European Union has their own version of it. Russia has their own version of it. China, Japan, India, there's different basically satellite positioning systems. The principle of operation is exact same. And in fact, the modern receivers use and acquire satellites for multiple global positioning systems beyond the GPS, and this is called the GNSS that we'll talk about. But again, we talk about basically the American version, which is the GPS, and it's the biggest one in terms of the coverage and the performance. But there's other versions of it operated by other nations. So again, it provides accurate, continuous global 3D position and velocity information, as well as what we call the coordinated universal time, which is related to that timing offset. Again, if you estimate your timing offset and correct for it, then essentially every clock on every device on Earth that is connected to GPS can be as accurate and perfectly synchronized with the GPS reference clock, which is this amazing byproduct. I mean, we think of GPS as just a localization technology, but actually the timing technology that comes is associated with it, and the synchronization across the globe of all these devices is as important and as useful as the positioning capabilities of it. Okay, another thing that's very interesting is that essentially because it's a one-way communication system, the satellite just broadcasts some signals and you use them to localize yourself and synchronize your time. It can service an unlimited number of users. There's, you know, it's like radio, right? It just broadcasts and then you receive it, so you can have as many receivers. There's no interference between the receivers or congestion of, you know, bandwidth, because the receivers do not need to talk to the satellites. It's just one way, which is very, very interesting. And also worth noting is that there is a worldwide ground control and monitoring network of stations that kind of communicate with these devices in the background, with these satellites in the background, and monitor their health, their trajectories, make sure they're fully operational. So there is a whole ground section to the GPS also, which almost nobody cares about, but it's really important to maintain and, you know, make sure the reliability and operational condition of the GPS. Also worth noting is that not all the satellites in the GPS system are the same. There's many different generations of these satellites. Now we are on the third generation of the satellites. Those are the most modern ones that we started launching them in late 2010s, I think. So these are very modern satellites. But there's still like Gen 2, different versions of Gen 2. These are called blocks for some reason. So there's, as of, I think, last year, there are 7 Block 2R. So Block 2 is like second generation, and R is for replenishment. So it was some specific version of the hardware. There were 7 Block 2RM. M is for modernized, and we'll talk about what we mean by modernization. 12 Block 2F, and just 4 Block 3. So they are still launching Block 3 GPS satellites, which has some interesting new capabilities. So they're kind of constantly, you know, upgrading the hardware, launching new satellites, adding capabilities, and so on and so forth. Some pictures of the satellites. They're not huge. They're just these like almost cube-looking, few meters across things with big solar panels. And I think 3 of them, A, B, and C, these are the second generation or Block 2 satellites, different versions of the hardware. And then this one is the more modern Block 3 satellite. Okay, so now let's talk about the signals that these satellites transmit. So as we said, the receiver needs to determine 2 things, or estimate the position of the satellites and also its range to each satellite. And the satellites transmit 2 distinct kind of signals for these 2 functions that the receiver needs to do. There is ranging signals, also called codes, and we'll see why they're called codes. And these are used to determine satellite to user range. And there's what we call the navigation signals. So the navigation signals are like data packets. So there's like human understandable information in them. It's like the internet data packets that you receive over the internet, right? So there's frames and there's, you know, different fields within each frame and subframe. And the navigation signals are used to determine the position of the satellites. Okay, the ranging signals, the reason they're codes, because these are mathematical codes. Like the ranging codes are not human understandable. You should do some math on them to be able to extract range. And we'll go in full depth on what the math is and what these codes are. But the navigation signals, you can interpret them, right? I mean, yes, there's like, you need to decode it correctly as the packets, but the satellite literally tells you, here is where I am at this point in time, okay? And that's how it's done. Okay, so more specifically, the ranging signals that are used, these are called pseudo-random noise, or PRN, signals or codes, and these are binary sequences. If you have not heard of PRN, no worries. We'll, again, fully in-depth talk about them and tell you what they are and why they're interesting. What's important, and today we'll talk a little about it, is that there's different ranging codes that the satellites transmit. There's like, actually there's a whole bunch of them, and we'll talk about them. And there's reasons why not just one. So there's, for instance, a ranging code that is for civilian applications. Then there's another ranging code which is more accurate for military applications, and they're very distinct. And there's different ranging codes on different frequencies, and then there's the legacy ones which were pre-2000, and then there's some modern codes that are transmitted. The principle of operation between like the military version and the civilian version and the legacy codes and the modern codes, exact same, right? But there is some functional differences, but you know, the math and the physics is exact same. So that's just worth noting. And the type of modulation that is used for most of these codes, as well as the navigation signals, is just binary phase shift keying, BPSK modulation. Again, if you're not familiar with this, I'll describe it for you. And both the in-phase and quadrature components of the carrier are used and typically modulated over. And in terms of the carrier frequency that the GPS uses, there's 5 distinct frequency bands. They're all between 1 and 2 gigahertz, but there's 5 different channels that all these GPS satellites use for communicating both the ranging signals and the navigation signals. And you might ask, okay, so there's something between like 24 at least to 30-something satellites transmitting all these different types of signals. There's like navigation signals, there's ranging codes, there's different flavors of ranging codes. So how do we do it on just 5 frequencies without these interfering with each other? And the concept that is used is called code division multiple access, or CDMA. And again, if you're not familiar with this, that's okay. We'll talk about it. But the core idea here is that the signals are mathematically orthogonal to each other. Although they're transmitted on the same frequency, they are orthogonal. And just like orthogonal vectors, you can distinguish them. These signals also, you can use this principle of orthogonality and distinguish the signals that you're receiving from different satellites, although they're all coming on the same frequency. Okay, let's have a quick look at the kind of like an idealized version of the GPS signal model. So here, this S of t is the signal that the satellite transmits. And as I said, it has 2 components. So there's an in-phase component to it, which is this first term. And then there's a quadrature component, okay? This should be familiar from communication theory. So each of them has basically, this is the carrier, which is just oscillatory signal, a cosine of 2 pi times the carrier frequency f sub c plus some phase. Phases, we don't care. The receiver really doesn't care. It's just for completeness in the model, we include that. And then the quadrature component, same thing. It's just a sine instead of a cosine, and that's how you get the orthogonality between your in-phase and quadrature, because the sine and the cosine at the same frequency, those are orthogonal functions. Then there's a bunch of things multiplying each of these. So first term, this root 2p, is just a number that's kind of like the power that you put in the in-phase and the quadrature components. So that's just a power. And then what's really important to us is these 2 signals. There's an x and there's a d, both multiplying the carrier or modulating the carrier. The x is the ranging code, okay? And then the d is the navigation signal. So again, just here is the summary of what I just said. And for now, just assume that the x and the d, these are just binary phase modulated signals, so as streams. So each, we start from a binary stream. So let's say your x of t. It's just some code, binary code, so just 0, 0, 1, 1, 0, whatever, right? It's a series of bits. That's a code. And then the way the BPSK modulation works is that wherever you have a bit 0, you map it to a phase of 0, so that's e to the j 0 or plus 1, and then wherever your bit is minus 1, the modulation is e to the j pi. So you either are at a phase of 0 or a phase of pi. So that's why it's binary phase shift keying, which is equal to minus 1. So basically, the actual modulated version of that x of t becomes, according to this, becomes plus 1, minus 1, minus 1, plus 1, plus 1, and so on. And then this stream is modulating the carrier. So the carrier is basically getting multiplied by a stream of plus 1s or minus 1s, which is the binary modulation. Same for the DI. Okay, that also is binary phase shift key modulated. Now you might ask, well, how do we, because at the receiver we need to decouple what's the ranging code and what's the navigation signal. And if both of these are just plus minus 1s that are multiplied by each other, how do we distinguish? And I'll tell you about it. It's actually a very simple principle, but for now, just bear with me. We'll get back to that. Now, note that this is kind of like the idealized signal model. In reality, the signal model is more complicated because we are not here modeling effects like the fact that, as I said, there's multiple codes being transmitted for ranging, for instance. We haven't modeled the noise, we haven't modeled interferences, effects like Doppler shift, timing jitter, or nonlinear effects. All of those are kind of factored out. It's fine. Again, with this idealized signal model, we can fully understand and analyze how the GPS works. But if you're interested, some parts of the slides, as you see, there's hyperlinks, and these are fully optional reads. If you are interested, for instance, this one takes you to this website, GNSS Software Defined Radio, which is this open source community of people working on GPS, and this one has like the full full-blown GPS signal model. If you're interested, these are optional reads for you. Okay, back to our discussion. Any questions so far about the signal model and this idea of ranging versus navigation signals? Again, I know this is right now, it's super vague. It might borderline not even fully make sense. We'll clarify all of this, right? So there's a lot to unpack here. But for now, at least the high level, there's ranging codes and there is navigation signals. And these are binary phase shift key modulated onto the in-phase and the quadrature components of a carrier at a frequency f sub c. If this makes sense, we should continue. But again, please, I really, really request at any point, if things don't make sense, stop me and just flat out tell me that did not make any sense, right? I owe it to you to make sure things make sense. And again, there's a lot here that we discussed. So for sure, at some point for each of you, some stuff should not make sense. So just to stop me right there and let's clarify it. Okay, so here's a high-level table showing, so as I said, there's 5 different frequency bands for the GPS signals. And this is a high-level table kind of showing how these frequencies are used. So the frequencies are called L1 to L5. And these are the exact frequencies of each. These are fixed, right? These are fixed. The receivers know them, and the GPS satellites never change the frequencies that they use. And then for each, there's basically in-phase and quadrature components being used. And here you have 2 columns. One says legacy usage, and one says modernized usage. So what this is that when GPS started, up till the year 2000, the signals that was transmitted by the GPS satellites, those are called legacy signals. And then in year 2000, there was this big modernization that happened for the GPS, and we will talk about it. And then what happened then is that a whole bunch of new ranging signals and navigation signals were introduced or added to the GPS system. And there were some hardware upgrades, a lot of algorithm and code upgrades, and that's what is the modernized GPS, basically. And we will talk about both the legacy and the modernized. Let's look at the legacy for now. So as you see in the legacy, the last three frequencies weren't even used for navigation. So L4 and L5 were flat out not used. L3 was just used for nuclear detonation signals, not related to us. And there were two signals transmitted on L1. One is called PY, and the other one is CA. I'm sorry, the notation makes absolute no sense here. I'll try to clarify it, but for some reason, when they were kind of like naming these ranging signals, they came up with these weird type of notation, but we'll clarify it. The P is for military use, and the C is for civilian use. These are the names of the two ranging signals. And then on L2, they were also transmitting the PY, and nothing on the quadrature, right? So in legacy, we had two frequencies for military ranging and just one frequency for civilian. And then for modernized, as you see here, a whole bunch of new stuff got added. I'll talk about these in a bit, but L3 is still not used for it's kind of reserved for some research applications and things like that, but not used for civilian or military localization. L5 also is being studies for some future, upgrades to the GPS system, and then L5 is actually used. So this is where we are with the GPS signals today. Okay. Now the next 5 or so minutes, I'm going to talk about all these different codes, which with weird nomenclature here. And it's a little boring, I'm sorry, but it's important. I think you should at least high level know what these are. I'll go quickly because there's like a lot of numbers that it's the kind of a thing that later in your work, if you need to know the specifics of the CA code, this could be your go-to place. That go dig up your EE259 lecture notes and find out what these are. But high level, each code, so start with the CA. So we're talking about legacy GPS ranging codes, not the navigation messages yet. CA stands for Course Acquisition Code. And again, this was a legacy GPS signal still being transmitted today. So today we're transmitting the modernized signals, legacy signals still being transmitted and relevant today. So it's what we call a short code modulated at 1.023 megabits per second. And it repeats every 1 millisecond. So the way these ranging codes work is that it's this binary sequence, and it's modulated at some baud rate, so in this case 1.023 megabits per second, and then it just repeats. So it's just periodically over and over and over again, exact same code is being transmitted. And that's the case for every type of ranging codes. These ranging codes are periodic signals that are just over and over transmitted. So this one repeats every 1 millisecond, which means at this bits per second, you get exactly 10,023 code bits, right? And by bits, I mean these zeros and ones, right? Those are the bits. They're also called chips. And you would see, I'll use the two terms kind of interchangeably. So bits and chips, again, if this is, say, your course acquisition code, I'm just going to draw the waveform for it. Okay, pre-modulation is just zeros and ones, right? So you have like 0, 1, 0, 0, 0, 1, 0, 1, and so on. Each of these pulses is called a chip. So that's what we mean by the chips. And then depending on your sampling rate, you might have just like one sample per chip if you digitize it. Or if you sample faster, you might have multiple samples per chip. But the chip is just one of these pulses or one of the bits in the underlying mathematical code. Okay? And each of the satellites, the 30-something satellites in orbit, uses a unique CA code. okay? And that's very, very important. So the code transmitted by each satellite, they all have the same number of chips. They're all modulated over the same frequency at the same baud rate, but the actual, that bit stream of 01000 is unique for each satellite. And that's how you distinguish it. That idea of code division, multiple access that I said is actually here. They use unique codes, and these codes are orthogonal to each other. Now, orthogonal, you might ask, how exactly, like, what do we mean by orthogonality? Because these are not exactly vectors that, you can do an inner product between. I'll clarify what orthogonality means, but for now, the concept is that each satellite transmits a unique CA code, and always that code. They never change their codes. It's part of the GPS standard that satellite block 2F number 3 transmits this very specific code, and the receivers know that. They have like this table hard-coded of the codes associated with every satellite. And it's, as I said, broadcast on the L1 frequency band. I found the first typo here, highlighted to correct it later. And please let me know as you find like typos and inconsistencies in the lecture notes so I can correct them. And it's for civilian use. Okay. PY, it's called the precision code, P for precision. I'm not going to spend too much time on it. It's faster by a factor of 10, so 10.23 megabits per second. It's also much, much, much longer than the CA code. I mean, look here. CA code was 1 millisecond. This one repeats every 37 weeks. Okay, so I don't know, like something like 12 orders of magnitude longer. So because it's so long, the satellites cannot store the whole thing. I mean, it's just too much memory for these satellites. I mean, it's like 10 to the 14 chips. So what they did instead is they have broken it into segments, and each satellite transmits a 1 week long segment of the full PY code. So unlike the CA, where it's a short code and each satellite has its own code, unique, to make PY unique between these two satellites, they took this giant 37-week long code, and then they chopped it into 1 week long sections, and every satellite repeatedly transmits a 1 week long section of the PY code. It's encrypted, so there's this cryptographic W code that is XORed with P code, and that's why it's called PY. So that's like the coded or version of the P. And it's supposedly robust to interference and spoofing, and as I said, it's broadcast in both L1 and L2 frequency bands simultaneously from each satellite. And it's for military use, so it's close to the public. Like our devices, our phones, laptops, they cannot acquire or use the PY code for ranging applications. It's only open to the military. And that's because this W code that is used for encryption is only known for military devices. Okay, any questions about, yes?
Then what is that on the receiver side, like the user, how to know the range of?
Oh, we'll get to that. So for now, that's a great question. So the question was, okay, so the satellites are transmitting these codes, which is these binary bit streams. How does the receiver use them to do time of flight ranging? And we'll get to that. That's a big part of this chapter in the course. That okay, how do you go from this bit stream to time of flight and then convert that to range? Great question, but bear with me. For now, we're just, familiarizing ourselves with like different codes and the terminology, but we'll get to the math soon. That's why this is the boring part. I want to get this over with quickly so we get to the interesting stuff. Okay, and navigation signals. As I said, there's two. Oh, yes, question.
Sorry, on the last slide.
Yeah.
Obviously, if the period is 37 weeks, how is that immediately useful to someone who's receiving a signal from you?
That's a great question. So I was told that I should repeat the question so people watching the videos know what the question was. So the question was, it's a 37-week long, say, code, or for each satellite, it's 1 week long, right? So how is it useful? Like, should the receiver wait for an entire week to receive one period of this code and then use ranging? I mean, that's useless. Great question. No, they do not need the full code. So the way the receivers operate for the PY code is that they can operate on short sections of the code. So they don't need they actually wait and acquire the minimum amount that gives them enough signal-to-noise ratio that they can use for ranging. And that's how it operates. The PY code, because again, it's for military, a lot is not known to the public about it. So like the exact code, of course, is unknown, but also some of the details of like how exactly what is, say, the minimum acquisition time that they need to do one position fix is not exactly known. But if I were to guess, it would be at most equal to the 1 millisecond for the CA code, or possibly even less. Okay, so the fact that it's just long, it's just helps them in the cases where the signal is very weak. Then you can just integrate or acquire a longer piece of this code to boost your SNR, and then you do acquisition. So they have this trade-off knob of either when the signal is strong, just do very short acquisitions and do ranging with that. When the signal is very weak, just capture a longer section of this weak-long signal and then do ranging with that, if it makes sense. Okay, great question. All right, let's talk about the legacy navigation signal. And the legacy navigation signal, it's called LNAV, L for legacy, NAV for navigation. And this, as I said, these are human understandable signals. So these are not like ranging codes, these are like mathematical bit streams. These are like data packets on the internet. And it contains three key pieces of information, the LNAV signals. One is the GPS date and time and the satellite's status. So the satellite says, oh, I'm healthy, I'm doing fine, you can trust this. Or when there's some fault condition happening, they flag some bits so the receiver knows, oh, this satellite is out of order. I should not use it for ranging. And then GPS date and time is just the date and time. When the packet is leaving or being transmitted, they just timestamp it with the GPS date and time. Then there's two other pieces of information, one called the ephemeris and one called the almanac. Ephemeris is very important to us, as we'll see, because the ephemeris is essentially the precise location of the transmitting satellite at the time that it's transmitting the signal. Okay? So the satellite tells you, the satellite is aware of their position with respect to the Earth, and they tell you that at this time that I'm sending you the signal, this is my exact position relative to the Earth. Now we'll see, the way they send it, for very good reasons, it's not like a XYZ location. So they basically describe their trajectory to you, not their exact position, because, again, the Earth is rotating, these satellites are orbiting the Earth, so by the time the signal receives you, the satellite has moved, right? And you sometimes need to account for that, so when you're doing your ranging. So instead of sending you an actual position, they describe their trajectory, and we'll see how it's done. It's very interesting. And then the almanac is basically the information about the rest of the satellites in the constellation. And it tells you, it's very low resolution information, so it roughly tells you like where the other satellites are orbiting and are they healthy or not. It's just used to kind of high-level check what the status of the GPS satellites are as we receive them. Now, I want to clarify one thing that I pointed out later, which is that, okay, so we have ranging codes and we have navigation signals, and both of these are modulating the exact same carrier, okay? So how does the receiver distinguish these? If you just multiply two of these binary sequences, so if I take this, so if that's my x of t, right? And then if I have my d of t, which is the LNAV, say, signal, right? So my x of t is, let's say, the coarse acquisition. My d of t is LNAV, another a binary stream, right? Whatever. 0, 1, 1. I mean, the specifics doesn't matter. But if I just multiply x of t times d of t, and just send that to the receiver, how does the receiver demultiplex? And because the receiver needs to separate out what's x of t and what's d of t, because x is used for range, and d, as we said, it has, for instance, the ephemeris data in it, and it uses d to find the position of the satellite. It uses x to find the range to the satellite, so it needs to demultiplex those. But if I just multiply these out, you cannot go back, right? So multiplication. So how does that work? It's actually very simple. The way it works is that, as you see here, the baud rate or the bit rate of these two signals is vastly different. So your coarse acquisition code, which is actually the slowest code that we send, as I said, is at 1.023 megabits per second. Okay, and then the LNAV is only at 50 bits per second, right? So 1 bit of the LNAV takes what? 1 over 20 milliseconds, right? So it's for a whole duration of 20 milliseconds, your LNAV is just either at 1 or 0, or the binary modulated version is at +1 or -1, right? Which is equal to 20 full CA codes, right? So basically, just by looking at different time scales, the receiver can distinguish the LNAV from the CA. Like if you just take a 1 second time window, 1 millisecond time window, during that, you can ignore the d of t, because that's just a constant, and the variations that are fast are just your coarse acquisition code. And the other way around, if you look at like very, very long time scales, then you can figure out what the LNAV message is. So that's how basically it's done. But this is how the transmitter basically combines the two. So you modulo to add or XOR the two binary sequences, and then just use one BPSK modulator to transmit. This is exactly mathematically, by the way, equal to what we had a few slides before. So what you get out of the modulator, this broadcast signal here, is actually x of t times d of t. But where your x and d, if you individually BPSK modulate them. So if you make your x of t go from 0, 1 to ±1, and also your d of t modulated to ±1, and then multiply them, that's exactly what you get out of this modulator. This is another way. I mean, different representations, same math. You can either XOR them and then just use one modulator, or individually modulate them and then multiply the outputs of the two modulators. Exact same. In practice, usually this is the implementation. Yes?
Can you go over one more time? What information is being conveyed through the coarse acquisition code?
What information? Okay, question. What information is being conveyed over the CA, or coarse acquisition code? So there is no human understandable information. It's just a binary sequence, seemingly random, of zeros and ones. Okay, and that's why it's called a pseudo-random noise, PRN sequence. And we will see how, from this pseudo-random sequence of zeros and ones, you can actually extract time of flight information and then convert that to range. So the CA, again, there's no human understandable information in it, but mathematically it's designed such that with some mathematical operation, you can extract range, time of flight, and then range. Okay? Again, it's very vague right now, but we'll get to it. We'll get to very specific mathematical description. And LNAV is just human readable, right? It's literally, numbers and things that one can understand. Okay, any other questions? No. All right. So let's quickly talk about this modernization that I told you about. So modernization, GPS modernization, was just this major, major overhaul of the GPS system across the board, from the hardware to the algorithms, the codes that were sent, what frequencies were used, ground systems, satellites, all of it was just went through this big modernization effort, which was one of the best things technology-wise that the U.S. I think government ever did, which was basically they authorized this modernization effort. It happened in year 2000, and it's also referred to as GPS 3. So third gen GPS is this modern GPS system. So again, there were new ground stations, new satellites, new civil and military, both navigation signals and also ranging codes. For instance, one of the big things that was added was forward error correction, which really helps in cases where you have weak signals. If you have forward error correction, you can recover. And I'll talk about what new civilian and military codes were added, but possibly the most important thing that happened as part of the GPS modernization was the end of what was called the selective availability, or SA. So what selective availability was that pre-2000, for civilian applications, the GPS signals were intentionally corrupted. So there was some jitter added to the GPS clock that was used for civilian applications, and basically that was done such that the civilian GPS was not super accurate because the government was not sure what types of applications people would do with this technology. Remember, this was a very new technology, and the government was being conservative with the civilian use of it. So they were intentionally, messing with the GPS signals by this thing called the selective availability. And the GPS really, by today's standard, pre-2000, GPS for civilian applications was useless. It was this super coarse, you could roughly tell, oh, I'm like within these 5 blocks of the town. So you could not do things like, Google Maps or anything really useful with it. At 2000, the government agreed that, okay, let's end selective availability. We are going to make the civilian GPS almost as accurate as the military, interestingly, as we'll see. And then that really was this really, really good thing that happened, and then that blew up these applications that we see around us today where GPS is extremely, extremely useful, to the point that even like indoors, sometimes in a big building, you can use your GPS to navigate around. The SA availability, so it was turned off, so disabled in all the satellites in orbit at the same time in year 2000. And the Block 3 satellites, these new satellites that are being launched now, they don't even have that capability. So for good, they killed it, which is very, very nice. Okay. A little more boring stuff. I want to quickly tell you about these modern signals that got introduced after year 2000. So there's a bunch of new ranging signals and a bunch of new navigation signals that were introduced. Specifically for ranging signals, 3 new ranging codes for civilian applications were introduced called L2C, L1C, and L5. And 1 new military ranging code was introduced, and a few different navigation signals were introduced. Again, let's not spend too much time on this because it's really just specs, not really quite relevant. I included these for completeness. But there's an L2C, which is called the second civilian signals. As the name suggests, this one is transmitted on the L2 frequency band, contains 2 different codes that are multiplexed on the same frequency, called civil moderate and civil long codes. Okay, these are multiplexed at 1.023 megabits per second. One is a 20 millisecond long code. The other one is 1.5 second long code. Okay. Now at this point, you might have seen a couple of interesting things. One is that all the codes we've talked about, in terms of the bit rate, there are some multiple of 1023, right? So we had like CA at 1.023 megabits per second, then there was a PY at 10.23, which is interestingly 2 to the 10 minus 1, and that's not a coincidence. We'll see why that's one of the magic numbers of these number of bits. So the power of 2 minus 1 is really deeply rooted into the mathematics of how these ranging codes work, and we'll talk about that. But these are not arbitrarily decided. These are determined by the mathematics of how these ranging codes work. The other one is that, as you see, the main difference between these codes is, well, there's two things. One is how fast they are in terms of the bits per second, right? Like the military code was 10 times faster than the course acquisition code. These L2C is almost the same speed. And then there's how long they are, right? So there's two factors for each code. And again, later we'll see both of these are important for basically the accuracy of how accurately you can determine your range to the satellite, and also the length of the code. So that's what the speed. Faster codes are typically more accurate. You can find your range more accurately. And then the length of the code, as I briefly mentioned, helps you with longer integration times, which means when the signal is weak, a longer code helps you do ranging because you have more signal to work with. You can integrate it for longer and recover signal out of noise. Okay, and that's why you have these different. So there's like the civil moderate signal, which is only 10,230 chips, and then there's the civil long code, which is like hundreds of thousands of chips. So the longer one, although it's at the same chip rate, so accuracy-wise it's the same, but it helps you when the signal is weak because you have more of these chips to work with to recover. Again, each satellite uses unique codes that are orthogonal, and this has almost 3 dB higher SNR than the course acquisition code at 2.3 dB less power. So it's quite a lot better in terms of SNR capabilities. And as of 2 years ago, there were 23 GPS satellites that where the L2C code was enabled on them. They tend to not, when it comes to these big upgrades, they tend to not flip the switch on all satellites at the same time. They kind of like do it over a number of years just to make sure, there's no glitches. They don't want to like jam everybody's GPS at the same time or something like that. They kind of are conservative with that. So it takes years. Although like the modernization was approved in 2000, it's still not, these new signals are not available on all satellites. Also, not all receivers yet support them. So chances are many of the, especially cheaper GPS receivers we use today, they're still working with the legacy signals because those signals are still transmitted and they're easier to work with. Okay, then there's a third civilian signal called L5. Same story again. It's two different codes transmitted on the in-phase and quadrature components of the L5 carrier. These are also at 10.23 megabits per second, 1 millisecond long, like the CA code. And there is basically some synchronization sequence also added to them to help the receiver more easily synchronize their times to the GPS. And then these also have 10x more bandwidth, 3 dB higher power, and as of last year, this was broadcast from 17 GPS satellites. Okay, and just now we're seeing some consumer devices using the L5 code. What's very important with the L5 code is that it has very, very good SNR. So it's good for basically secure and robust localization for safety of life applications. So people, for instance, who do extreme sports, people who go like mountain climbing or they go like hiking in very remote areas, they usually have these fancier GPS devices with them, which are L5 enabled, because those are the ones that can save your life in very remote applications where GPS reception could be pretty poor. So that's important. And just now, as of like last year or so, I've seen a few more like cheaper consumer grade devices that claim they're L5 enabled, which is very interesting. Okay, and then there's the fourth civilian signal, L1C. This is transmitted on the L1 carrier, as the name suggests, kind of like the L5. This is also two codes modulated on the INQ components of the carrier. Both are 10 milliseconds long, same number of chips. What's different about the L1C, it uses a different type of modulation. So it's not binary phase shift keyed, it's some different type of modulation, which is called binary offset carrier, or BOC. And again, you see these are like slight variations they're doing on these codes. Each adds like a benefit in a certain use case. Some are good for low SNR cases. Some have better accuracy for ranging. Again, the BOC is more energy efficient. You know, it's just these slight variations that they're doing to different modern codes, just to ensure, you know, more availability, more universality across, you know, use cases, across locations, across devices. That's basically the idea. But underlying, like, if you abstract out all the little details of like what the code is called and what exact modulation is used, and go down to the core mathematical principle of how these operate, as we'll see, they're exactly the same, identical. So we will just look at the CA basically, because everything else is identical to that. Okay, and there's a new military code called M. There's absolutely almost nothing known about it, except that it's at 5.1 megabits per second, BOC modulated, and it has a new navigation signal associated with it called MNAV, M for military, and it's broadcast on L1 and L2 frequencies. Other than that, there's really not much known about the M code. One interesting thing with the M code is that, so the way these satellites broadcast their signals is they have antennas that are very wide in terms of their beam. So if this is the Earth, and this is your little GPS satellite orbiting, pardon my bad drawing. Generally, the antennas they have, because they want to have as much coverage as possible, so they have these super wide antenna patterns that kind of like cover as much surface as is visible to them on the Earth. So they have very wide. Now, what they did with the Block 3 satellites for the M code, they have an additional antenna which can do kind of like a much tighter localized beam transmit just for the M code. So it's almost like a separate antenna that does that. And this one can like be much more localized, which means it would have much higher power density per area, which means much higher SNR. So what they can do is, I think they can boost the SNR by 20 dB, which is a factor of 100. It's a lot for military applications in very localized areas, which is, of course, a huge military advantage that the U.S. military has. Okay, and then there's, as I said, new navigation signals also as part of the GPS modernization. The core idea is the same. So the navigation signals, same information. They send you the GPS time. There's an ephemeris which tells you where the GPS is, or the orbit trajectory of the GPS satellite. And then there is an almanac which tells you the status of the rest of the satellites in orbit. But the modern ones are, again, they're better. They have like error correction. There's some changes or some upgrades to the data structure. So they're packet-based instead of frame-based. Honestly, I don't know why that's better, but apparently it's better. And also, for instance, the almanac now supports up to 64 satellites. So in case later they decide to put much more GPS satellites in orbit, the almanac data frame has now the capability of providing the status of up to 64 satellites. And there is also a CNAV2, again, another navigation signal for civilian use, modulated onto the L1C code. All of these are very similar, slight variations in terms of like what type of error correction coding they're using or what is the exact bit rate. But in principle, they're all transmitting the same information, which enables you to determine, most importantly, the location of the satellite, but also, you know, information about the rest of the constellation and the GPS time and so on and so forth. And then there is a MNAV for military navigation signal, We don't know any details except that it is packet-based and uses some type of forward error correction. Okay, enough boring stuff. Any questions? No, again, you don't need to like remember or know any of these details. It's kind of a thing that I wanted you to kind of like go through it once, so these terms at least are familiar. So if you hear like, oh, there's like L2C coding signal, then you say, oh yeah, I've heard of it. I think I know what you're talking about, but mostly for reference. So if the specific thing you're working on, I don't know if you're working on some next-gen GPS receiver or some other project, then you can refer to these and kind of like get the specifics of these ranging codes that you want. Okay, this is the same table we saw before, but hopefully at least these names are familiar to you. So as you see now, if you look at the modernized one, L1 is pretty busy. We are transmitting a lot of stuff on the L1. So there's still the legacy military PY code. There's a modern military code. There's the L1C D, which is the data part of the L1C on the in phase. And then on the quadrature of L1, we have the legacy CA code for civilian, and then the modern L1 also for civilian. L2 also kind of not as busy, but there's a bunch of things. There's the in phase is military only, the legacy and the modern, and the quadrature is for civilian only. And then L3, L4, again, as I said, they're not used for localization, but they're reserved for some other applications. And then L5, purely for civilian use, both in phase and quadrature. And also, it's important for like those safety of life type applications. It has the best SNR capabilities and some safety features associated with it. I think it's also good to take a look at what the power spectral densities of these signals look like. So the way to look at these plots here, let's look at just this one, top left one. So this is showing as a function of frequency the power of these different coding signals that are modulated onto the L1 carrier, right? So the way to read this is there's two planes. One here, the vertical plane is sort of your, say, I channel or in-phase channel, and then the horizontal one is your quadrature channel. And then this axis here is frequency. So 0 is the center frequency around carrier. So this one is for L1. So what 0 really is, it's not DC. It's like the center L1 frequency. And then around it, as you see, we are roughly using about 30 megahertz bandwidth, right? Plus minus 15. That's how much bandwidth we are roughly using. And each color corresponds to a different code that's being transmitted, say, on L1. And there's some interesting properties, I think. Let's just inspect two of them. So if you look at this darker green one, that's our CA code, right? And if you remember, it's one of the, or actually the slowest code at one megabit per second. And as you might remember from signal processing or communication courses, slower signals don't have less bandwidth, right? So how fast you, the bit rate of your signal, that directly correlates with the bandwidth. And as you see, the green one, it's kind of narrow. It has like this very narrow main peak, which is actually just around 1 megahertz, 1 to 2 megahertz. And then it has a bunch of side lobes right around it, quite a bit down in terms of power. And if you compare that to one of the fast codes, say pick your PY code, this one here, which is this darker brown color. PY code, if you remember, that was 10 times faster, right? That was modulated at 10 megabits per second. And here you see the main lobe of the PY code is much, much wider than the CA. So at least qualitatively, these make sense. As you make your code faster, it takes up more bandwidth or takes up more spectrum. I should probably have used this one because it's less busy, but same idea. Again, here you have your M code that is pretty wide, right, because that's a fast code. And then you have your L2C code, also a slow code, and that's the main peak is much, much narrower. But again, this is just qualitatively you see how the spectrum is used and how much power and bandwidth each of these codes are taking on different frequencies. So we have L1, we have L2, and we have L5 here, which is the least cluttered, I would say. And then L3, L4 are not using for ranging as of now, so that's why there's no picture for them. Questions? No. Okay, so let's continue. There is two different types of GPS services which directly relates to like these ranging and navigation signals that we talked about. One is called PPS, or Precise Positioning Service. So this is enabled. This is military stuff, right? So it's enabled. The ranging is done with the military codes, which is either PY or the modern version that is the M code. And then the navigation of it uses the military again, either the modern MNAV or the legacy LNAV for military. And this is highly encrypted, and only authorized military devices can use it, and has all sorts of safety military-grade features like anti-spoofing and so on and so forth. And the nominal accuracy of it is 229 meters. So that's your localization accuracy. So you can localize yourself within a circle or a sphere of a radius that is 229 meters. Okay, so it's pretty good, but also I should note that it varies a lot. So GPS accuracy, there's a lot of different factors that affect your signal quality and ultimately affect the localization accuracy. So these are nominal numbers. In worst case conditions, it might be 10 times worse than this. In absolute best case conditions, it can be even centimeter accurate. Okay, so it really, really depends on strength of the signal and a number of other effects that we'll talk about. Then there is the standard positioning service, which is what all the civilian devices use. And this, as we said, it can use any of the civilian codes for ranging. I think today, probably most devices still use the coarse acquisition, the legacy signal, but now we're transitioning to either of these, L2, L5, L1, and then it uses either the CNAV or the legacy LNAV for navigation messages. It's open to the public, so these days you can even do like a DIY project and pretty much build your GPS receiver from scratch. It becomes a very big project, actually, but it's could be fun, but every detail of the civilian stuff is known, from the detail of the codes, the communication details, packages, the error correction codes. It's all very well documented, so you can build your own thing. And accuracy of 5 to 10 meters. So what's very interesting here is if you before I learned about all this, my expectation was, or I was always under the assumption that the military stuff is much, much, much more accurate than the civilian. It's not the case. Actually, the accuracies are ballpark the same for both. And this is thanks to, by the way, turning off the selective availability. Before that, civilian was much worse, but now ballpark the same. So why have the distinction? Well, the military stuff has a bunch of extra features that's why it's important. So, for instance, the ephemeris updates, which tells you where the satellite is, come much more rapidly for the military GPS or the precise positioning. It's more robust to some of these effects that degrade the GPS signal quality. One of them, for instance, being the ionospheric delay. So ionosphere is one of these atmospheric layers above the Earth, and it's pretty notoriously troublesome for GPS signals because the frequency of the GPS signals lies in a band where inside the ionosphere, the speed of light can change significantly. So there is this unknown delay. If we go back to our time of flight principle, one of the underlying assumptions was that this C is constant, right? But it's not actually constant because the medium changes. You go through different layers of the atmosphere, especially the ionosphere, depending on the incidence angle, can cause some additional delays in your GPS signal, which translates to range inaccuracies and ultimately positional inaccuracies. Now, the military-grade GPS, it's much more robust, for instance, to this effect, right? There's, as I said, there's encryption, anti-spoofing, so you cannot, spoof it easily. But at the end of the day, remember that civilian GPS and military GPS, nominally, they are exactly the same accuracy, which is a few meters. That's what you can expect. Now, regarding the accuracy, like, is it good enough or not, really depends on your application, right? Of course, I think we can all agree that GPS is extremely, extremely useful, right? Both for human applications and for robotics, but it's not enough. Like the level of localization accuracy that you get from a GPS receiver, it kind of like globally roughly positions you on a map, like you can know you're at roughly this intersection, in a city or around some block in a town. But if you were to, for instance, use only this to fully automate your robot's movement, it's not enough, right? So it kind of gives you global, as the name suggests. It works globally. That's the amazing thing about it. And globally puts you on the map. But you still need much, much, much more accurate localized local measurements with other sensors to further narrow down your location inaccuracy from a few meters down to a few centimeters possibly, or even millimeters. It really depends on what the application is. But if you're in very tight spaces and your robot needs to like navigate really intricate structures, you need much better than a few meters. So that's where this idea of, for instance, sensor fusion becomes important, and that's why you need a variety of sensors. Each has its own unique capabilities, but ultimately you want to combine what you get from all these different sensors to really get to what you need for your specific application. Okay, questions? No. All right, we have a couple of minutes. I just want to set up the discussion for next time, which is we're going to now talk about the actual math and physics of GPS, starting with the satellite orbits. Again, the first step, as we said, is that your receiver needs to find the exact location of each of these GPS satellites that are orbiting the Earth. And in a way, the satellite tells you where they are, right? But you still need to do quite a bit of math to convert that information, which is what we call the ephemeris, which is part of the navigation message, to the exact location of the satellite. And it involves, you have to have a model of what this orbital trajectory looks like, which usually it's modeled by, not usually, always, it's modeled by an elliptical trajectory. But this needs to be done very, very, very accurately. So it's actually a pretty challenging problem. You have this satellite 20,000 kilometers above you, going at very high speeds. You're on Earth, that's rotating. There's a variety of forces that affect the satellite, from Earth's gravitational force. There is solar radiations. There is the emission of different gases from the satellite that can, change its trajectory. So there's all sorts of different effects that make this trajectory not be a perfect ellipse. And you receive this very, very slow message. Remember, the navigation messages are transmitted at 50 bits per second. So it can take minutes to receive enough information of like one ephemeris, data point. So that's where a lot of brilliant engineering has been done, such that with such a slow communication channel on the navigation signals, you can still super accurately and very quickly track the exact position of the satellite. So that's what we'll discuss next time.